see about 15, 16 people on Zoom. I think we're not live yet, am I right?
So we're in live, sir.
Oh, you've gone live? Okay. All right. Good. Welcome, everyone. We should be about to start. So let me just share the screen with the presentation. So hopefully you can see the slide here. This is the live session. So some of you might remember, some of you may not. So you need to join two different things. One is this WebEx to listen to this audio. The other is joinpd.com. So you need to go to joinpd.com and put in this code. The code is on the top right, HYMNLM. And then all the responses to the questions that are put up, you have to do that on the joinpd.com app. Okay. So I'm not sure if you've had experience with joinpd.com or not. I think some people use it. Some people maybe don't. I don't know. You can tell me if this looks very new to you. Hopefully let me type in the website and the code here. So joinpd.com is the website. And the code you have to use is HYMNLM. Okay. Okay, let me just stop sharing for a little bit. So I hope this joinpd.com is clear enough. In case you have any issue with it, please type out a chat message. Otherwise, I'll assume that this is okay. Okay, so this doesn't work. Okay, so you see about 20 people in the session. It's better. I see about 21 people in the session who've signed up. So please go to joinpd.com and then put the code HYMNLM. So maybe this is all the people we'll have. So I'll wait for just a couple of more minutes before beginning. See, I think you will need your online degree ID to log in. People logging in. Okay. So if you're watching it on YouTube also, I don't know if you can see the website. It's called joinpd.com. And then the code is on the top right, HYMNLM. Okay. So code is on the top right, HYMNLM. You have to go to joinpd.com. I don't have a way of typing into the comments on YouTube in case you're logged in only there. Please go there. Okay, otherwise you can't participate. The answers you write in YouTube are invisible to me. I can only see them on those on join PD. So I see there are 44 or so participants. Let me share my screen. Okay, so you can see the code on the top right. Those of you who are on Zoom, you can see it on the chat also, HYMNLM. Okay, so let's begin. This is almost the end of the Stats 2 course. I hope you've learned quite a few things, lots of topics, new and different topics when compared to Stats 1. In particular, in this live session, I'm going to focus mostly on estimation and testing. Okay. I'm assuming you've gone through some of the lectures. You have a basic familiarity with the different ways of estimation, different ways of testing. I will talk about some of them briefly, but I'll assume you've seen the lectures a little bit and focus on a little bit more of hands-on practice in the live session. Okay, so let's begin. In the first slide here, I have two things. One is a sheet containing formulae for hypothesis testing. Can you click on this link? I'm not sure. I think I've shared it on YouTube. I'm pretty sure. I've shared it on Zoom. Can you confirm with a chat message or something if you can click on this link and it works? Okay, you can. Okay, good. So there are two things here. You have to do two things. First is you can click on that formula link and get the formulae. And more important is the survey form. Okay, so you have to click on the survey form. It will ask for your online degree login. I think it should. And then there are three very simple questions that you have to answer. Okay, so we're going to do like a live data collection exercise as part of statistics 2. As you know, it all starts with collecting data. So click on that survey form, go into that survey. There are three very simple questions and answer them. Okay. The first question is about whether or not you're currently enrolled in a physical program in a college. That's the first question. Second question is your age. And the third question is your CGPA in the program. Okay. So we're going to collect this data and make some statistical calculations around it. I wanted to give a feel for how this data collection exercise would work. So the link is on this slide, and people are telling me that they can click on it. If you can see the slide, there are two links on it which are in green font. And I guess on Peer Deck, you can click on it. So if you had gone to joinpd.com and then put in the code HYMNLM on the Peer Deck site, you should be able to click on these links. Maybe not from Zoom. I think Zoom just shows it as video. You won't be able to click on it on Zoom. You should go to joinpd.com and then put in the code HYMNLM. Then on Peer Deck, you can put it. So the first exercise we're doing is data collection. Let me check on how that is going. I think I need to exit from screen. People are supposedly responding. Let me see. Oh, I've got 38 responses already. Oh my God. I thought it will go slower than that. Okay. All right. I think 38 is a lot of responses. Maybe I should close the sheet. Let me just see the responses. Okay, you can see some people are putting in wrong values here to make life difficult for me. But mostly people have done a good job. I think they've answered correctly. It's about 45 already. Maybe I should stop accepting responses. Is that good enough? 45, 46? Have people, is that everybody? I think I saw only about 40 people on the, oh, it's 57. Okay. So let me just wait for a few minutes for people to put in the data. Okay, I think 50 is plenty. I think, let me just make sure I have enough variety here. Yeah, I think there's enough variety here. There's enough and more variety here. Okay. Okay. So I'm going to stop maybe accepting responses. I hope everybody has put in their responses. Thanks for doing so. So let me just say stop accepting responses. There you go. Okay, thank you. Thank you for the participation. So here's the data we got from 49 people have responded. Apologies if you got in a little late. And you see, of course, you don't see who they are. You just see their answers. So this is how a typical sample collection exercise works. Maybe not as simple as this, but anyway, nevertheless, you can see how it works. So we're going to use this data. I'll keep coming back to this data window whenever I need it. It's okay. So let me just keep it like this. I hope you can see this more clearly. Let's go to the first question. I hope everybody's ready. Let's go to the first question I have for you. So this is an estimation question. We are interested in estimating the fraction of learners in Stats 2 who are currently enrolled in college. This is what we're interested in. As you know, there are more than 2,500 learners in Stats 2. Some of them are currently enrolled in college, some are not for various reasons. We would like to know the fraction of learners who are enrolled in college, and there is a survey form. Of course, you can't click on the survey form because it's not when you can click, but you can't put in a response now. So on peer deck, the first question is this: which question in the survey is important for this estimation? There are three questions: the first one, or the second one, or the third one. Okay, so it's an easy response for you to write. I'm just getting you warmed up. It's an easy question. Which question in the survey is important for the estimation? So remember, there are only like 49 people who responded to the survey. So clearly, we have to do something statistical to estimate the actual fraction of learners who are currently enrolled in college. But nevertheless, which question in the survey is important for this estimation? So it's a easy enough question, I think. None? Somebody saying none? Why no? Don't put the answer on the chat window, by the way. You have to respond on peer deck. Okay, so I think it's more than 30 responses now. I was hoping more people will respond because there are some 57 and it's a simple enough question. There are three questions. The first one asked directly whether you are enrolled in college or not. I would think that would be a very direct clue. The second one was about age. Third one was about it was about CG. So for trying to estimate the fraction of learners, what would be the correct thing? So let's see the responses. Let's see something a little bit better. Okay, this is a little bit better. People are saying the first question. So it's sort of very clear. The question. So some people are saying age. Okay, well that's an interesting point, isn't it? So is age a good question to determine this? You can't say no, isn't it? I mean, age is maybe something you can use. That's an interesting point somebody has made. Think about why age is relevant, because one can assume that the younger people are going to be in college. But yeah, definitely. But there's a more direct question which you can use directly. Okay. So now that you had this, so I'm going to share the survey results. And the next question is actually two questions. What is the method of moments estimator for the fraction? And what is the ML estimator for the fraction? So I have to show you the data. Here's the data. You can see the answer to the first question. I hope you can see it. So let me just zoom a little bit. 150, maybe 200. So I don't know what's the easiest way to transfer this to you. So you can see maybe what I can do is the following. Let me do the following. Okay, so I'm going to share this sheet with a link and put it on chat. Okay, there you go. So you will need the online degree ID to see this content, but I hope you can see it. Okay, so you have the sheet with you. There's 49 pieces of information here, and you can see yes, yes, no, 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 and you can use Google Sheets calculations if you like to do something. So based on that, you have to now answer on peer deck. How many? What is the fraction? What is your estimate? For the fraction, I mean, I've said estimator. I mean, I can put in the estimator. Basically, it's you should tell the estimate also. What is the M method of moments estimator? What is the ML estimator for this fraction? Says action denied. Really? Okay, let me just check. Okay, so maybe it's a different group or something like that. I think let me just make it open to all. So
you have to click on the share with Indian Institute of Technology.
oh, I didn't do that. Is it? Okay. Okay, yeah. Sorry about that. Yeah. Now you should be able to access. Try again. Try again, please. Yeah, I see a lot of letters there. So I think people are able to access. That's good. Okay. Oh, some people answered without even accessing the data. How was that possible? You would wonder we're using intuition to answer. So remember once again, there's 49 people who responded to the survey, and there are 2,500 learners in class. What is the MM estimate? What is the ML estimate for the fraction of students who are enrolled? Just use the first column of data and answer the question. I don't know if it's easy for you to count. Maybe I should count. So count. S is at 30, no is at 20. Yeah, so I've given you some viewing options, which makes it a bit complicated to do your own filtering and all that. It's shared with too many people. So yeah, there you go. Abhishek Gupta is helping everybody, which is what I also did. So 30 is S and 20 is college. Okay, so don't put your answer on the chat window. You need to enter it on peer deck. Okay, so you go to joinpd.com. Answers have to be presented there. Enter the code HYMNLM. I see about 6 people have responded. See, about 11 people have responded. So this is the sheet which has the data in case you would like to access it. I'll wait for a couple of minutes. I hope the estimator is clear. This is a yes/no question. So this is a Bernoulli P estimator. So the way you have to think of this estimation is each student in the class of 2,500 is this x1, x2, x3, so on, right? But you don't, of course, sample everybody, right? If I had data for everybody, there's no need for statistics. If I have 2,500, I have only 49. So people who are in this call are the actual x1, x2, x3 till x49, right? So imagine that, keep that in mind. Each of you have to think of as someone who randomly chose to attend this call, right? So I'm just randomly deciding that each of you, you've come in here, it's like a Bernoulli P sample. So if you're from college, I've sampled a 1. If you're not from college, I've sampled a 0. So I have x1, x2 till x49. Each of them is Bernoulli P, and this P is the fraction I'm after. If you said yes, it's 1. If you said no, it's 0. So for 49 IID Bernoulli samples, you have to simplify in P. Okay, so it's one of the standard problems in estimation. There's enough responses now, so I can go see. 29 by 49, about 58%, 59%. Correct, 30 by 49. Yeah, so something of that type for 29 by 15, 49, 30 by 50, roughly 0.6 is the estimate. I think many people have got it. Maybe you're thinking about it, and there's more detailed explanation from someone on how everything is derived and all that. That's great. So in simple terms, you have to assume each a random student being in college is with probability P. That's the fraction P that you're interested in. And I just did a survey to pick some 49 people at random. I'm hoping at random, right? So out of that, how many are actually in college? So we're sort of saying that that fraction is representative of the overall fraction for 2,500 also, even though I had never asked all the 2,500. Okay. So that leads me to this next question. Think of this very carefully, okay? We just did something, right? We just did something and estimated something. What are the assumptions I have to make about the survey and the data that I got for this to be a valid sort of estimate, or at least a reasonable estimate, right? What am I assuming, right? I have to assume, first of all, that each of you uniformly at random, each of the 2,500 uniformly some sort of at random decided to attend or not, okay? So it could be that more people who are not in college are able to attend this live session than people who are in college. Maybe there are some things like that, but I'm ignoring all that. I'm just saying everybody is uniformly likely to come, or my sampling is very random across this 2,500. If not, then estimating this will go wrong, right? So actually more important than the calculations that you do to find that 29 by 49, these kind of questions are more important in real life. But of course, for the exam, you have to get the 29 by 49 right. So I won't diminish the importance of getting the fraction right. Sample is chosen at random. I think that's IID. All of that is extremely important. Once you assume that, things are okay. So hopefully that part is clear. So always, whenever you do a statistical estimation problem and you're collecting data or looking at data, think about this. I mean, what can I assume reasonably about the data? That's something very, very important. Okay. So all the other questions will be like this. You will have to use data from the sheet that I gave you. I think it's not very immediately usable. So maybe I should share it a bit strongly with more people in case you want to. Let me just see. Or I think you can you can copy this into some other sheet which you can edit, right? Is that correct? Can you confirm that you're able to make a copy of the sheet or download the sheet? Yes, so please do that so that you can edit your version. I don't want to share this version for editing to everybody. Let me keep this with me. Please go ahead and make a copy of this sheet so that you can play around with that data in case you have to add it, square it, do something. It's easy for you to do it on the sheet itself. Okay. Okay, so let's go on to the next question. We'll do a series of estimation and testing problems using this data. So let's use this data and do it. So here's the next question. I'm interested in fraction of learners above 60, okay, in class. The fraction of learners who are above 60, okay. So the first question asks you to type out, how will you modify the survey data to estimate this quantity? Okay, so how will you think of the survey data? Survey never asked this question, right? We didn't ask, are you above 60? But we did ask something else, and that is definitely equivalent to this. But you have to do some small change to make a modification to the data that you collected. And what is that modification? It's a simple question just to get you warmed up. Hopefully you'll get the answer right. I'll just wait for 10 responses and then show the responses to you. Here's 10. So let's see the responses. Filter out above 60 learners. So filter and find age greater than 60, right? So you convert the number that you got into a 1 or a 0, okay? So once you do that, you can estimate, okay? So I've asked two questions here. What is the ML estimate of the fraction? Okay, what is the maximum likelihood estimate based on the data that is there on the sheet? And what is the Bayesian estimate with a uniform prior? Okay, that's your question. So I think this data is probably this, I see a 50, but I think 50 is the max, probably. Yeah, max is 58. Okay, no one above 60, but look at that. There's 58, there's 50. Okay, anyway, what is the ML estimate? What is the Bayesian estimate? I'll give you the truth also because I have the data of everybody in class. So I can give you, maybe I can't tell you the fraction, but I can tell you the maximum actual age after you give me the two fractions. Okay. So no one above 60, that's correct. So the ML estimate should be trivial. Maybe you're confused about the Bayesian estimate. So if you remember Bayesian estimates, if you have a uniform prior, you have to add 1 to the, so if you have x1, xn being Bernoulli P, so Bayesian uniform prior, the estimator is x1 plus xn plus 1 divided by n plus 2, right? Hope I got that right. Yeah, that's the estimator. So the ML estimate, I think the ML estimate is easy. ML estimate is, we have seen this, we have done this before. ML estimate is just xn divided by n. Okay, so each xi is Bernoulli P. So now P is the fraction. This is the fraction with age greater than 60. And these are the samples, right? So we got 49 samples. So our n would be 49. Okay. So remember n equals 49. Okay. So in the past, I've had this question saying, why should n be 49? Shouldn't n be 2,500? Because there are 2,500 students. Okay. But remember, n is the sample. If you could get the data of 2,500, then you don't have statistics at all. It's just you can just do data crunching to get the exact number. So we don't have 2,500. So we have only 49, and we're trying to sort of extrapolate statistically. There are different ways of extrapolating. One is just ML, which is no extrapolation in some sense. Otherwise, you should do this. Okay. So let's see. There you go. Okay. So see, I've asked you for uniform prior. Okay. So there's no beta 1, 51 and all that. It is just, okay. So look at that. Look at this answer. 1 by 2,502. Why is that wrong? Why is that wrong? He has put n equals 2,500. Really? Do you think n equals 2,500 is correct? Think about it. There is only 49 samples. Okay. Your n is 49. Keep that in mind. It's 2,500 is the total number. ML is 0 and Bayesian is 1 by 51. Okay. So 0.019. That's correct. Those are the correct answers. Keep that in mind. This is a common mistake using 2,500 instead of 49. But remember, if I had 2,500, I won't be estimating anything. Okay. I have all the data, right? So hopefully this is clear. I just wrote down the formulae here. You can once again check this. This is the formulae. So each of the samples in your case was actually all 0, 0, 0, 0, 0. You got 49 zeros. Your Bayesian with uniform prior will say 1 by 49 plus 2. That's 1 by 51. ML estimate, of course, will say 0. Okay. What do you think is the ground truth? Can somebody guess? Do you think there are actually 0 people above 60 in our stats 2 class this time? What do you think? What do you think is the, actually it's not 0. Okay. The ground truth is the maximum age is actually 75. Okay. And at least 10, I think that's correct. There are at least 10 people above 60. So what goes wrong, right? What do you think went wrong here? Should we throw this out? No, actually look at the Bayesian methods, right? So the Bayesian method has actually given you a reasonable estimate. In fact, it says 1 by 51. Yeah, population taken was small. Yeah, true. But still there are estimates, even with small sampling, they're able to give you something reasonable. So that's why it's dangerous to just use ML estimate all the time. Okay, so you have to account for what you could not have seen because of the small sampling. Okay, many of these ML estimates and all that work when you really use a lot of samples. But if you have only very few samples, these modifications you made with Bayesians, with prior, using some other information is very, very important. Okay. So hopefully this is a good example to drive home the point of why all this +1, +2 and all is important when you have very few samples. Okay. How did you decide on uniform prior? Yeah, it's just a random choice. Not random. I mean, when you don't have any other information, you have to decide on uniform prior. Okay. So if you have some other prior information, so I'll give you a non-uniform prior example. But I just decided on uniform prior. It's a safe thing to use. It's flat. I'm not biasing in any particular way. But actually, uniform prior is not a good prior for this problem. Why is that? Can somebody say why uniform prior may not be a very good thing? What else would you use? What information, what data you will look at to decide a better prior? Can somebody suggest something? Is there some information you have about ages are not uniformly distributed? That's true, no? So how would you look? Where would you go to look, to adjust your prior distribution of age of where? Where will I go to look for this data? Well, okay, so supposing I want some first order information, we can make a histogram of what? Population data. There you go. That's close to it. Population data of India, right? At least for prior, the only thing you can use is what fraction of people in the country are above 60? What do you think is that number? You can Google it immediately. Okay. So maybe you want to use a prior which gives more importance to that fraction, right? It biases you towards that fraction. So that kind of thing you can do, which is what I've done here. And that brings me to question There you go. He's done the Google search and just put it out, and you can see where I got the 10.1 from. Okay, so you can search for this, and then try and have a more informed prior. So previously we had a very less informed prior. It's just a flat prior, and then somebody brought up this point that why should I choose uniform? Maybe I can choose something else. So don't worry so much about the distribution. I'll come to it. The distribution for age in our class is actually not normal. I've looked at that also. So the age in our class is not normal. I don't know about the age of any population. It's whether it will be normal or not. It's a bit difficult to judge that. It's not really like independent things are adding. So age distribution is a little bit more complicated. But anyway, so given that the fraction of senior citizens in the country is 10.1, how would you use that information to come up with an informed prior? So I want to use a beta prior, and I'm going to put alpha, and I'm going to pick the beta parameter of beta as 4. Okay, so you must know the formula for the mean of a beta distribution. It's alpha by alpha plus beta. So given that I want 10.1%, I have 10.1% senior citizens in the country. How would you inform your prior? How would you change how would you pick the alpha to use this information? So remember, when you use CLT, you have to have a sense of many random variables with same distribution adding independently. Okay, I don't know if you can say that for age. I don't know. So it's usually a difficult distribution. It changes a lot in different countries. There is an average age, of course. For our country, it's very low. And, I don't know about India's histogram, but definitely in class, the histogram cannot is far away from normal, because there'll be a heavy weightage to the young population, right? In class, you can imagine 17, 18, 19, 20, 21, 22. Under 30 is very, very high. And then there is a small decaying tail. It goes on all the way till 75, 60. So yeah, so to answer Steve Richards, yeah, so that's all you have to do. So you take the mean of the prior and equate it to the mean of what's expected in the country. So that's what I would do, right? Not posterior mean, this is prior mean, right? So the prior mean can be 10.1. This is a reasonable assumption given the problem, right? So it's the overall in the country, the fraction is 10.1. So if you want to put a prior, you want to put a prior that keeps the average at 10.1%. So you can pick an alpha which has alpha by alpha plus 4 equals 0.101. So you'll get a solution for alpha. Use that. So I don't know what alpha people are getting. So that's the question I've asked. I hope that's clear. Okay, I think Steve Richards, you're confusing two things. I did not calculate 10.1% from the sample. See, from the sample, the answer is 0. There's nobody above 60. Right now in this live session, there's nobody above 60. Okay, where did I get the 10.1 from? It's population data. It's independent population data from census in the country. Okay, in the whole country, fraction of people who are above 60 is 10.1. So one thing one can do is to pick a prior which has 10.1% as the mean, right? Yeah, so somebody else is suggesting, if you get better data, can you get better priors? Yeah, absolutely, right? You can ask better data and get better prior, but given that this is all the data I have, you just use it, okay? Okay, so let's see the responses. Okay, so wow, 404 by 9899.45. 0.44. That seems to be the consensus of 0.449, 0.45, 0.449. Yeah, that seems to be okay. So the way I would do it is as follows. So I would say if you want beta alpha comma 4 prior, the mean equals alpha by alpha plus 4, which is 0.101. Okay, so is that correct? Beta equal to 4 is an arbitrary choice. Yeah, true, absolutely. You can if you have additional information, you can use a better price. Okay. Is this okay? Is this the equation you got? Alpha by alpha plus 4 equals 0.101. How does this solve to? Okay, so if you do this, I think somebody had put 404 by something else. So you'll get the answer. I think this is roughly about 0.5 is the answer. Okay, I hope that's all right. Okay, so hopefully this is a little bit different from your problems that you solve in your usual assignments. So it should help you. Okay, so let's move on. So here is a model that I think is a little bit maybe more appropriate for the age of students in stats 2. So I'm going to assume that the age of learners is 17 plus Poisson lambda. Okay, so you might say, why don't you assume Poisson lambda? Because Poisson lambda will start at 0. And I know for sure that the age of people in this class is starting at 17. So there's no point in doing something crazy from 0 to 16 and then only putting Poisson lambda. So I'm going to say the age of learners is 17 plus Poisson lambda. Am I sure that Poisson is the correct distribution? Probably not. I would argue there are other maybe distributions you can pick, but why not? It's just an estimation problem. So assuming this is the case, what is the ML estimate of lambda? Let me see. It needs a small modification to what you've seen in class. So you can make a small change in the quantity we asked for in the survey. We asked for something, and then what you got was the age, right? 23, 25, 18, like that. So you can do a small modification to get a Poisson. What I'm claiming is a Poisson, and then try and fit the lambda to it. Okay, hopefully you made a copy of this sheet. Once you made a copy of the sheet, you can do calculations on it directly. Yeah, so I think you could think of it as adding something to the likelihood also. Yeah, you can also subtract 17 from the samples, right? So you can subtract 17 from the samples, and those will have to be Poisson lambda samples. And from there, you can estimate lambda. Okay. So the samples you got are 17 plus Poisson of lambda, right? So if you subtract 17 from the samples, you will get Poisson lambda samples. Okay, once you have Poisson lambda samples, you can just estimate lambda directly. Is that okay? needs a very simple computation, which I hope you can make on the sheet itself. I mean, you can, if you have a new sheet, you just have to write a small formula involving these things, and then you'll get it. Hope it doesn't take too much time. Well, estimate for Poisson is something I've done in class, so you might remember the estimate for lambda. I think if I'm not wrong, it's 1 by sample mean, isn't it? Yeah. So just have to find sample mean, and then we'll subtract 17 from the samples to get Poisson lambda samples. Find the sample mean, do 1 by that, we'll get the estimate for lambda. Oh, lambda is the sample mean itself. Yeah, sorry. Yeah, you're right. Sample mean itself. It's not 1 by, it's the something else is 1 by the exponential. Okay. True. Yeah, absolutely. Thanks for correcting that. Okay, I'll give a couple of more minutes for people to get to this. Okay, so let's see the responses. Wow, very long response. What happened to that? I don't know. My goodness, somebody has kept on typing enter, is it? All right, so let me not do this. Let's try this one. Oh, that doesn't work at all. Okay, let's see. He has completely muddled up the answers. Is this some sort of a strategy? I don't know. Who is this? Please don't get everybody confused. 26.7, 9.59 seems to be a popular answer. So some other people have got 26.24. Oh, I think you're adding 17 to your answer, is it? You don't need to add 17 and say 26 as the answer, right? I think the answer should be 9 point something. Because you're subtracting 9 from it. It's just estimating lambda. So I think there's no need to do that. Okay. Okay, so I think it's not 26.59, it's 9.59. Okay, because I mean, I think some people are adding the 17 and giving the answer, but I'm just estimating lambda, so that needs to just be 9.59. Okay, yeah, so sort of like that. Yeah, if you did the overall sample mean, you would subtract 17 to get 9.59. Okay, you can also find the overall total mean and subtract 17, or subtract 17 first and then find the mean. It's all the same. Okay, so there's still a question on why are we subtracting from mean. See, the distribution is 17 plus Poisson of lambda. Okay, so every sample, age sample, is actually 17 plus Poisson of lambda. Okay, so if you find the mean, let's say you're doing sample mean, it's like the sample mean of 17 plus Poisson of lambda, which is like 17 plus lambda, right? So lambda's estimate, you have to subtract that 17. Okay, think of why that is true. Okay, if you had Poisson of lambda samples directly, then the sample mean itself is good enough. But you have 17 plus Poisson of lambda, so it should be 17 plus the estimate, which is the sample mean. Okay, so think about why that came about. Okay, I hope that's clear. Okay, so now quite often people ask, why do you fit a distribution to samples and find the distribution? So it turns out one can use if you believe that you've done a good job of fitting, okay, like I just wrote down 17 plus Poisson lambda is, I think, a good estimate for the way in which this model works. If you believe that you've done a good fitting for the distribution, then you can use it to estimate probabilities that you did not see in the samples, right? So we saw that we did not have 60 plus in the sample, but there are people who are above 60. So maybe one way of doing some estimation of that type, if you have a good belief that this Poisson lambda is a good sample, like good model, may not be a good model in this case, but nevertheless, you can use this distribution to make predictions on people above 60 or even above 70 or even over 80, who knows, right? So so somebody is asking me a question about other distributions. So the way to think of the 17 plus seems to be confusing everybody. So maybe I should spend a little bit more time on that. Okay. So I have 49 samples of 17 plus some distribution, which means I have 49 samples of that distribution itself, right? I subtract 17 from the samples. I get 49 samples from whatever distribution I assume. Okay. And then those samples I can use to estimate the parameters I want from the distribution. Okay. So keep that in mind. So if instead of Poisson I used some variant of gamma or something, then it's more difficult to find mean and all that. It's a bit more complicated, but otherwise it's straightforward to think of this as 17. And another question on why I added 17 in this model, because my assumption is there's nobody below 17 in the class, right? So might as well give Poisson a bit of a shift, because otherwise Poisson starts at 0, right? So I add 17 to Poisson, and Poisson may increase and decrease a little bit. So it might be a truer model. I'm just guessing. I mean, it's just a guess. I mean, you can argue either way, but 17 plus is a better model, I think, than just Poisson lambda. Okay. I hope Advi's question also got answered. I think if you have any other constant plus some sample, you simply subtract that constant from all the samples, you get samples of that distribution, right? And then you're back to estimating whatever that distribution is. So it's the good old classic problem. Okay. So now we have to consider age. Okay, everybody's so totally taken up by this. Okay, no. Okay. What is so somebody is asking about, should we consider 70 plus 17? No. The age itself is actually 17 plus a Poisson model. That's my model, right? So 70 will be equal to 17 plus some Poisson distribution. That's how I'm thinking about it. Okay, the simplest logic is simply subtract 17 from the samples. You get back to the original, some sort of the samples from some distribution, and then you do the estimation. 17n plus likelihood of Poisson, that will need some, for Poisson it might work, I think, I'm not sure, but for other distributions you might have to derive something. Okay. Yeah, sure, you can think of it that way, but I think I really like the subtracting 17, going back to that distribution and then doing whatever you want with that distribution. Okay. Okay, so the actual answers are a bit complicated. I think I see a couple of responses. I don't know how they did it. You'll have to do some calculations. Oh, 0. It's not 0. Really not 0. How did you get 0? It's actually a 1 minus CDF evaluation, right? It definitely can't be 0. Okay. So if you now have 17 plus Poisson of lambda as your model, number of people above 60 is like 1 minus Poisson CDF evaluated at 60 with that lambda, right? You will get something, isn't it? It's, I think Poisson CDF, I don't think there's any closed form expression. So you'll have to use some numerical tool or something like that, or write a more complicated expression. Sum from 71 to infinity. Yeah, that's true. Okay. 43 can't be the answer. I'm asking for a fraction. Is that okay? Do you see why it can't be 0? I mean, it's not 0. Poisson distribution doesn't die out. So it dies out very slowly. So you have very, maybe quickly, but it dies down. It has a tail. So you have to add up from 61 to infinity. Okay, so maybe I should. Here. So if you have being Poisson lambda IID, okay, the ML estimate for lambda is x1 plus xn by n, right? It's the sample mean, right? So that part is clear. So now instead of Poisson lambda, if I have this plus 17, right? What does that imply? This implies I can't say this anymore. I can't say this directly anymore. So what I have to do is I have to say x1 minus 17, so until xn minus 17 is still IID Poisson lambda. So lambda hat ML is x1 minus 17 plus dot 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 xn minus 17 divided by n, and that's x1 plus xn by n minus 17. Okay. So this is how you find lambda hat. Okay. So once you found this, okay, probability that age is greater than 60 is actually probability that 17 plus Poisson lambda is greater than 60. So this would be probability that Poisson lambda with whatever lambda you found is greater than 43. Okay. So this is just a CDF computation, right? So you need to do so 1 minus CDF of this Poisson lambda evaluated at 43. Is that okay? I think there was a question from Huzaifa Taher. I don't know. I hope if that works out. Okay. So you just do this, you'll get the answer. So I mean, this is not an easy expression. You've got to calculate this. I mean, there's some numerical tool. Let's tell you what it is. I think this lambda came out to be close to 9.59. So you have to do 1 minus CDF of this Poisson at 9.59 evaluated at 5. Is this okay? So for 70 also, I mean, I don't think it's the, well, CDF of not Poisson, that 17 plus Poisson evaluated at 70. So if you want just Poisson, it's evaluated at Poisson CDF. Does it need a third parameter? I don't know. Somebody can look it up. Can you not ignore it? It doesn't work with 2 parameters. Okay. What? So let me just check. Maybe somebody can answer. Steve Richards wants me to give up the exam question. No, there's no one about 70. No, I think I think it's one because of accuracy issues. It's not really one. I think it's just numerical accuracy issues. Okay, so can ignore. Okay, so anyway, so this kind of thing is very common. So for instance, people always want to know whether an earthquake that might occur in a particular place will it ever go above a certain number on the Richter scale or something. So if you want to model that, you are in this kind of territory. So you sort of model some phenomenon and make predictions on. So the constantly something will get registered on the Richter scale, right? I think you might probably know that it's not like you never have earthquakes. Earthquakes are constant. And the thing is, does it cross a certain number on the Richter scale? So that's a extrapolation type problem. So this is very typical in those kind of many such problems. You want to have a model, a probabilistic model, then make predictions on whether it will go above something or not. Okay. So remember this formula is just a numerical calculation. Maybe it ends up being close to zero, but if you do better accuracy, calculate better, you will get some very small number. I think Poisson falls off very fast, so maybe it's not a good model, right? So maybe you want some other model. I mean, I think the falling off exponentially is maybe not very good. So you need some other model here. It may be very small. Okay. No. In exam, you won't be asked to do any such crazy thing. Don't worry. You only have the TCS calculator in the exam. Whatever you get there, you'll put. Don't worry. Okay. Okay. So, by the way, my live sessions, I do it partially for the exam, but mostly I try to give a bit of a flavor of the kind of things you have to think about. I think most of you are looking for a shortcut to exam questions, and I'm sorry, I'm not giving you that shortcut. I'm telling you something about estimation and testing. I hope it's useful in the way you think about these ideas, and that's always good. Okay. All right. So I think we're going to move on towards testing. This is the this I think, or maybe there's one more. Oh no, we have moved on to testing. So testing always involves hypothesis. Thanks, Sadhvi. I think don't worry about such calculations. It's just something. Okay. So testing, on the other hand, involves these kind of statements, right? So one of the statements might be the average CGPA of learners in stats 2 is below 7.5. Somebody might say that. It's in this case, it's about CG. You can imagine other populations where people may claim the average IQ of people in one particular state is below something, above something, whatever the average. I don't know. So many other things people may claim, and quite often you have to verify these kind of statements. And in fact, a lot of statistics is around verifying statements like this. It has direct impact on policy and various other things. So this question in the survey that we collected, etc. Actually, you design the survey after you decide how to answer the question. But now, anyway, so given that we have CGPA information, this is a very natural question also. So if you were to answer this question, what will your null hypothesis be? What will your alternative hypothesis be? What is the test that you will use? What will be your test statistic? Okay, so I can see responses coming in slowly. Okay, so once I get about 20 responses, I'll show. Let's put 17. Let me give a few more minutes. Okay, so I think we've sort of saturated at 19 responses. I'm not getting the 20th one. So let me just show what the answers are. Okay. Okay. So yeah, I think the null has to be mu equals 7.5. Okay, so the null is always sort of like the static one. You want to make the null as the simple hypothesis. You don't keep the um, composite hypothesis as null usually. So some people will argue you should say it's less, but no, I think it's equal to is the null and less is the alternative. I think that's correct. And standard deviation is not given, so you have to use the t-test. So it's just the single sample t-test and reject null. Reject null if the sample mean is less than 7.5. I don't know, some C, right? You don't know what the threshold C is. You set some threshold C, calculate sample mean, and it is okay. 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 So okay. So I think this some it's a little bit complicated to figure out the alternative sometimes. The null, you always usually want to take it as a simple hypothesis. So I think the null most people will agree is average equals 7.5, right? Now, alternative has to be, you know, less than 7.5. Because I want to have the statement, the null get rejected and the alternative gets accepted to prove the statement, right? So that's typically how people go. No, you always reject null. I mean, you make your test to reject null. You can, of course, also make a test to reject alternative, etc. But I think it's more common to think of it as rejecting null. Your test criteria should reject null. If your test statistic is less than or greater than something, you reject null. Is that okay? I think that's the best way to have some consensus on how null and alternative hypotheses are chosen. So your test is the t-test. In this case, because standard deviation is not given, and your test statistic. What is the test statistic? I think not many people wrote what the test statistic is. What is it's a sample mean. I think you can see somebody has written here. The test statistic is the sample mean, so you can use the t-test. Okay, good. So now the next question asks you for what is your conclusion at a significance level of 0.05. So here you have to assume a distribution and was to assume normal distribution. Okay, so there's a question from Puneet. I think it is a little bit confusing. So I mean, don't think of 7.5 as the threshold. The way I would think of it is somebody is casting aspersions on the learners in the stats2 group and saying their CG is very low, and but our normal assumption is the CG is quite good, 7.5. So we say 7.5 is the null. That's the normal hypothesis. It's good. And the alternative, which is sort of, I only want to accept it with small probability, right? That's the mean is less than 7.5. So usually you don't think of 7.5 as the threshold. It's sort of like the what you're testing for. The threshold actually is on the test statistic. You have a test statistic, which is the sample mean. In this case, it will be, you have to go to the table here. and look at the CG, and then look at all the 49 GPAs, and then take the sample mean of these guys, right? That will be your test statistic, which is capital T. Now, how do you decide to reject null? You reject null if T goes below some C, right? That C is going to be something below 7.5, right? But how far below it will go will depend on the significance level, and the significance level is the probability of rejecting null, given that null is true, right? So that's the calculation you do for the alpha. So I hope that's clear. So that's the type 1 error. Yeah, so that's true. I think it's so what Puneet is saying is you want to say the null is mean less than 7.5. So usually people don't take the null as the composite hypothesis. Typically, you want the null to be, if it's possible to take a hypothesis to be null as simple, the null hypothesis is simple, you should probably take it that way. You can ask, of course, there's no unique way to answer this question. I will sort of agree with you. There is no unique way to do it. So in an exam, most probably we won't ask too many of these type of questions, but it's important to follow some convention. The convention is if you can pick a simple hypothesis as null, you should pick a simple hypothesis as null. Okay. So in this case, mean equals 7.5 should be the null hypothesis, and the alternative should go to mu less than 7.5. Okay. So again, it is convention, but it's a very commonly used convention. So I think you should pick it like. Okay, so maybe it's worth writing down the formula that I wrote here. So there are these samples. So I'm saying these are n equals 49 samples of CGPA that we collected just now. The null is so I'm going to assume these are IID normal mu variance sigma square. Okay, null is mu equals 7.5. Alternative is mu less than 7.5. So significance level alpha is probability of. Okay, so before that I should write the test. The test statistic is sample mean, which we know is going to be normal with mean mu and variance sigma squared by n. Okay. But in this case, I need the sample mean to be calculated, and I will also need this S squared to be calculated, right? The sample variance. Okay. And then I will use the t distribution, x bar minus mu by s by root n is t48, right? So people are giving the sample mean and the sample variance, standard deviation. So you can use that. Then you have to do a lookup on the t distribution to get a significance value of 0.05. Is that okay? So you will reject null. The test is what? If t is less than c. Oh, no, sorry. T is that correct? T is less than c. That's good, no? Yeah. That's going to be your test. Sample mean, can it be 26.59? Are you looking at the age or are you looking at the CGPA? This is CGPA, right? So your sample mean cannot be 26.59. That's like way too high a CGPA, or unless somebody entered something above 10. So sample mean will work out to be 8.1. Okay, that sounds about right. Okay, that's good. Variance is 0.91. That's good. Okay, so I'll leave you to do the calculation. I think most of you have sort of got there. I've done enough calculations like this in the thing. I think since the standard deviation is 8.1 and the variance is 0.91, you really, yeah, I think sample mean is already gone above 7.5. This really, like Abhishek Gupta is saying, absolutely, there's no need to do any calculation after this. You will accept the null. Okay, so you will never ever go rejecting null. Okay, so the C will always be less than 7.5. So there's no problem. Okay, so we will accept null. So the average CG is above 7.5. Okay. It's okay. The sample is what you have, right? I don't know. I think it might be slightly better. I think the average that I calculated with all the data I had came to around 7.6. So so maybe the better students are attending the live session. Okay, it's all right. It's not too bad. Okay, so let's go to the next question. The next question is going to give you slightly more calculation. So I think we're a little bit out of time, so I'm not going to give you too much time to calculate. Just think of how you would answer it. So for the same problem, if you want if you assume standard deviation is 1, and then if you want a significance level of 0.05, okay. Did you need the normal distribution? Yes, no, didn't you need it? Usually the t-test, people use it all the time, but I think it's the proof for t-test comes from the normal distribution, right? I think the sample variance having the t-distribution is peculiar to the normal distribution. So I think you do need to assume it, and most questions in stats will not even ask you to assume. They'll just give it, and you just assume normal. And it's okay, but still, I think I'll just put it there. Is that okay? So I think you do need the normal assumption for things to work. Okay. Okay, so significance level 0.05, and supposing you want power of 0.95 against 7. Sample distribution is always normally approximated. Not always, of course, there's all sorts of exceptions. But in some cases, in most cases, yes. Okay. So CLT is usually what's used. So if you don't have the assumptions that justify CLT being true, then you'll have to look at your assumption. So CLT is whenever you have IID samples adding, independent identically distributed samples adding, then definitely normal is a good approximation for sampling. Okay. So this is a calculation that you can do. I'm not going to do this in detail. I think I've done this. I've shown it in class how this power equation works. So maybe I'll just depict it with one picture and then leave it at that. Let's go here. Oh, okay, so so basically you have on one axis. So let me just show you just how to visualize this power and all these things, I think. So you have 7.5 here. I'm not drawing very much to scale, so don't, just for illustration. So I have 7 here, okay? So the normal distribution works something like this, right? So I've said, as in taught, the standard deviation is 1, right? So this is normal, mean 7.5, and standard deviation 1. Okay, so maybe I can take a different color here. So maybe a red color. So this is the alternative distribution against which I want some power, right? So this is the alternative distribution. Okay, so I'm going to have some C here. Let's go back to black. So I'm going to have a C here. Let's say this is my, this works out as my C. So I'm going to reject null if my sample mean goes below C, right? So this is 1. So I'm just working with one sample here. This is like n equals 1, right? This is because it's where I put 1 there. So my what would be this area? Can somebody tell me what will this area be? So in terms of alpha, which is the significance level, what would be this area? The area to the left of C. Yeah, it's just alpha, right? So this will be the significance level. Where will power come? What will be power? So which area will be power? Supposing I have to show the area for power, which part will I add? So it's the probability of rejecting null given that the alternative is true, right? So that would be this area, isn't it? This would be beta, right? Beta or 1 minus beta? 1 minus beta, right? I always get confused with this. This is beta or 1 minus beta? Beta is the type 2 error probability. So 1 minus beta is power. Is that correct? No. Is that 1 minus beta? Is that correct? Yeah, okay, 1 minus beta. Most people agree 1 minus beta. That's correct. Should be correct. Okay. So now what's wrong with this situation? It seems to give you very high alpha, very high beta, right? But how do I improve it? What happens as n increases? So supposing n becomes 100, how will this picture look? So this is for n equals 1. Which picture? This picture and this picture. So n equals 1. So when I do n equals 100, what will happen? Both alpha and beta diminishes, yes, but how will the distribution look? So this is the distribution of the sample mean for n equals 1. What will happen to the distribution for the sample mean when n is 100? It will have the same mean, but its variance will really go down, right? So, I mean, 100 may not be, so maybe I should just say it's 10, okay? 10 itself is good enough, okay? So it will go off like this, something like this, okay? Not to scale, I'm just drawing it. So the mean remains the same, but the variance will drop dramatically, okay? So it will go off like this. I'm drawing the thick one here, so you can see how it will go. So this is for n equals 10, okay? So this is n equals 10, and that guy is n equals 10, okay? So you can see for the same threshold C, both the area, the alpha area and the beta area have shrunk to something very small, okay? So this is the effect, this is the picture that should remain in your head when you're thinking of hypothesis testing with this just a single sample mean type testing, okay? You have two parameters, alpha and beta, which are these two areas around this threshold line C, around the test statistic threshold line. So, and by increasing number of samples, you're decreasing the variance. This PDFs shrink and the areas change. Okay, so this picture with the area is something very important, and I hope you retain this in your head. I think more than anything, this is very important to think of. Okay. All right, so let's move on. So once you have this, I think 0.95, 0.05, you'll be able to do this calculation. I'll refer you to the notes. There is a calculation for how to find number of samples. So this is very textbook. I think this is one of the most textbook calculations you can do. You should be comfortable when you do that. Okay. Okay, so let's move on. Okay, so Adhavi is asking a question which is probably one of the most difficult in statistics. If you're given samples and you think your hypothesis is reasonable, how confident can we be? So these are tough questions. I think it needs a lot of experience. Generally, these kind of numbers people take to be as very good. Significance level of 0.05, power of 0.95. These are all taken to be good. If you can manage testing at that level, then great. But today's problems, given the amount of data we have on the large the dimensions that we are dealing with, this is tough. So what about, okay, is there a way to say my sample is a good representation of the population, right? So how do you say whether your sampling is good or not? I think that therein lies the difficulty. I mean, very renowned statistical experts make mistakes in that. It's very, very hard. I think if you can get, so particularly in a country like India, you want to take any statistic, you can pretty much get any number you want by sampling cleverly. So it's very hard to say do that. It's very, very hard to do that. It's a very tough problem. There are some very established procedures. You have to use them and hope for the best. Okay, I mean, I can point you to books, etc., which talk about how to do this. Okay, but time and again there are mistakes of this nature. Sampling goes wrong. So you should talk to many people in India. I think, I mean, including people here. They will have one data point of one type of medication that worked, right, for one of their close relatives. And you should see the confidence with which they talk about that medical practice and say, this is the method for curing this disease. You should see it. I'm sure many of us have met such people who talk like that. So one data point of one close relative is sufficient for them to be so confident. But Adhavi here is so careful. She's learned Stats 2 properly, and she's really, trying very hard to get the thing right. But I will tell you, this is the difficult part. Okay, so you have to be very, very careful, question the sampling a lot, understand whether they've done it correctly. It's very, very difficult. And most people have a certain ideology, and they will, use sampling in a clever way to push the ideology. I think it's very sad. But I mean, now that many of you know Stats 2, maybe you will ask the right questions. But it's a lot of it is outside of statistics in some sense. You can't, once the data is there, you have to work with the data. You can't do anything else. And you have to have a good working knowledge of the world, so to speak, to question the statistical methodology. And a lot of mistakes have been found in statistical sampling. Okay, anyway, so that's a topic for a different day. Let's move on. Okay, so here is an interesting proposition. Okay, someone says learners who are currently enrolled in college have a better CG on average than those who are not. Okay, again, it's just an ideological statement at this point, not even ideological, just somebody's belief. Somebody is making a statement like this. Among the learners in Stats 2, those who are currently enrolled in college have a better CG on average than those who are not. Okay, so this is the statement. Now, the first question is, do we have some data in the survey that we did that can help in answering? In case that is true, what would that data be? What will the test, what is the test that you will use? And what is the test statistic? By the way, you may also have an ideological belief on whether or not the statement is true. Okay. So quite often it turns out statisticians get biased by those ideological principles, and that can make, force you to make mistakes in the direction in which you're biased is. There's even a term for that, by the way. Okay, so I was, I'm sorry if this was not conveyed to you or not. I was planning on a 2-hour session, so 7 to 9. So we're doing decently on time. So that's why I'm spending more time here. But I do realize it's a tough time for people to be around. We'll see. We should be wrapping it up. I think we have just 3-4 more slides to go. So it should be okay. Yeah, these slides will be shared on the portal for sure. Okay, so let me show the responses in the interest of time. Okay. Okay, people are talking about correlation and all that. Yeah. Okay, so this is actually a 2-sample problem. Yeah. 2-sample mean test problem. Yeah, X bar minus Y bar. Yeah, absolutely. Okay. So do you have both samples? Did we get 2 samples? That's the question, right? Do we have 2 samples? Right? So we didn't, I mean, there are 2 samples here, right? So you go back to this. So here's your thing. So you know, people who said no, that's about 20 in number or 19 in number, something like that. And then you go find their CGs. That's one sample. And people who said yes, and then go find their CGs, that's the other sample. So you have about 30 samples from one group and 20 samples from the other group, right? So it's a 2-sample mean test, comparison test. Okay. So sample mean of one sample is X bar, sample mean of the other sample is Y bar. And the test statistic is going to be X bar minus Y bar. Okay, so I hope you got that right. I think some people have written that down clearly. Maybe they didn't say what X is and what Y is and how many samples of each they have. So maybe I should just write that down. So remember there is this thing we have. So you have black. So we have x1 comma x2 n1, which we're going to assume is normal, mean mu 1 and variance. So I think, I don't know if some assumptions were given in the question. Okay, so maybe they're not given in the question. So, but we'll have to eventually assume something like that. mu1 sigma squared. Then you have another set of samples, which is 2 sigma squared. And so H0 is mu1 equals mu2. Okay, so this could be in college. This could be not in college. And HA is what? Mu1 is greater than mu2. Okay. So your test statistic is going to be X bar minus Y bar. And you reject null if T is greater than C. Is that okay? I hope it's okay. So now this T is going to be given H naught, it's going to be normal with mean 0 and variance sigma squared by n1 plus, okay, actually you can put sigma 1, sigma 2, like sigma 1 squared, sigma 2 squared by n2, right? Is that okay? So the statement says it's not equal. I mean, it says it's have a better CG. So better is greater. So that's what the statement says. I hope this is clear. So you see how you have to unpack the statement that you want to show. So why is there no mod in the test statistic? I think you can't have mod. I mean, it's X bar minus Y bar. I want to see if it's greater, right? It could be lesser. If it is lesser, then you're in trouble. Okay. So the next question says survey results are shared. You assume normal distribution and you find p-value for both p-value for the test. Okay. So I think n1 was 30 and n2 was 20 or something like that. Okay. What happened? What is the confusion? Yeah, it's a one-sided test. So it's X bar minus Y bar. Two sample mean test. Okay. Is this okay? Okay, so think about it. So the statement claim is on average, those in college have higher CGs than this. Okay. So I don't know if 1 plus CR and all is going to come. So that comes in the ratio test, right? It's in the other test, the variance test. And I'm not testing for variance here. Okay. It's not testing for variance. I'm testing for the mean. On average, I want to claim that people who are in college have. Okay, so there is a next test that's coming up, which will be on variance. Okay. Yeah, I think it's confusing that there was a document that I shared much earlier, which had a list of formulae and all that. So Shreyans is asking a question, what is so great about 0.05? I mean, it's just a value. Some people take 0.01, 0.03, even take 0.05. Many people take it. People accept 0.05. Okay, nothing beyond that. Okay, so I don't know if you had the energy to do the calculation or not. You'll have to find the probability for alpha. Yeah. So the document that I shared with you earlier in the session, that will be shared in the exam also. So you don't need to mug up all the formulae there. That will be given. So you can, so for finding the p-value, you just write down the formula for alpha and substitute, instead of C, you substitute the actual statistic that you got, right? So by the way, did anyone compute the test statistic for our sample? Did anyone compute this? I'm curious to find an answer to this question, so that's why. Is that quick to do? You have to first filter on one column. Yeah, so you put a mod if mu1 is not equal to mu2, right? So if the alternative hypothesis is mu1 not equal to mu2, then your test statistic will be absolute value of x bar minus y bar. If my alternative is mu1 greater than mu2, I have to have my test statistic as x bar minus y bar and reject null if t is greater than c. Isn't it? See, notice the logic of this is it's not very illogical in some sense, right? See, if my null hypothesis is true, then t has to be close to 0, right? If my alternative has to be true, then what should t be? T should be positive, right? So if t becomes larger and larger and positive, I want to accept h naught, right? No, for x bar minus y bar, I don't know if I. So is that clear? So if given the null hypothesis, mu1 becomes equal to mu2. So because of that, the difference x bar minus y bar will be normal with mean 0. Okay. So remember that. So given the null is mu1 equals mu2. So that's what gives you 0 here, and then the variance will just sum up. So there you go. So Advi has managed to calculate it, 8.105 and 8.109. And so okay, so there you go. So the answer is clear. You don't need to do any testing. This is minus 0.004. So okay, yeah. So you will accept the null hypothesis. You will not be rejecting it, and you can find the p-value for it if you like. Okay, so that's what would happen. Well, I don't know. I think I've heard enough people talk about p-value. So I think it's complicated to. In real, college goers have lesser CGPA. I don't think it makes a big difference is what this data is telling you. So we'll have to see. Okay. There's a question about spending some time on p-value. I don't know what kind of question you have in mind. I think I see it as just another way of characterizing significance value, if you ask me, right? So I think it's just historic why p-value is used, why something else is not used, and all that. In general, p-value actually is defined using significance value, right? There is a significance value, and then you substitute instead of the threshold the sample mean you got, and then that sort of gives you one strange probability. Some people say it's some extreme case. That's the worst possible case in which your null is going to get rejected, etc. So a very low p-value means you reject null, and then high p-value you accept null. It's I don't know if one can say much more about it than that. How did I? So you can calculate. I think you can calculate, but it's negative. But yeah, you can go ahead and calculate. But I think I don't know. So you can calculate the p-value. My guess is it will get rejected, but I could be wrong. You should check it. I just put it out there. Okay. Okay. All right. So let's move on. Oh, so Puneet is contesting the calculation. I think since he is not currently enrolled in college, he has got an answer which is significantly higher for the non-college goers. Is that right, Puneet? So anyway, you can check it. It's lower for non-college. All right. Okay. So he's giving the opposite answer. So I think Advi has to maybe check out. I mean, I think it's getting late, close to 9. So let me not check this. If you're very keen, you can start a discourse thread. I'll definitely answer there. I think this is interesting that the CG is lower. I'll do some more digging and find out how big that difference is. Okay. Okay. All right. So let's move on. Here's another statement. CGPA of students enrolled in college varies less widely than those who are not. Okay. So assuming the mean is the same, okay, which is not stated here, you can do this F test here. The answer for this would be the F test, which was somebody was you can do the F test. Anytime you want to say the variance is lesser or greater, you will have the F test coming in. Okay, so take a look at that. That should help you. I'm not asking for any calculation here. It's just you can look at it and do the F test. Okay. So the last two questions we don't have too much time on, but I'm going to I'll leave it at this. This also needs extensive calculation. I'm not sure if you are ready to do it. So supposing I say the mean of the actual mean of the CG, I want to model it as say normal with mean 7.6 and standard deviation of 1. Okay, and let's say 100 samples I've got. So actually we don't have 100, right? We have only 49. Okay, so you might have to revise this. And let's say I'm trying to see a fit for a normal distribution with 7.6 as the mean and 1 as the standard deviation. How do you go about checking this? So for this, one needs to use this kind of a table, right? You classify the CG into different ranges, less than 6, 6 to 7, 7 to 8, 8 to 9, and greater than 9. And find how many you expect under this distribution, normal 7.6 and standard deviation 1. Okay. So it turns out you can do these calculations, right? It's just a CDF calculation with normal. You are expecting about 38 in the 7 to 8 bucket, 26 in the 8 to 9 bucket, greater than 9 in the, you're expecting about 8, less than 6, you're expecting about 5, and 6 to 7, you're expecting about 22. Okay, so this is the case. So now you have to go to the CG table and fill out this next row, which is the actual frequency that you saw here. Okay, so how many people got less than 6, how many people got 6 to 7, like that. Okay, and then what test will you use to determine goodness of fit? There's a standard test here, chi-squared, right? Chi-squared, and then what would be k? K would be chi-squared 4, right? Because there are 5 values here. There are 4 degrees of freedom. So you'll use chi-squared 4, and then you can do your test. Okay, so this is how you can check. I believe the CG is close to normal. You should be able to model it well as a normal distribution. You should get some reasonable value for that. Okay, so this is Q7. And the final question for the night is a very interesting question, which you can again test out from the 49 samples that you have, whether it's true or not. Somebody might want to ask, is age independent of CG? Okay, again, you may have a lot of ideological and other beliefs from your past experience, but what does the data say? Does the data say age is independent of CG or not? How does one prove this? Again, you have to make a table, but this time it's more of a matrix. You put the range of CGs on one side, and then you put the ages on the other side, and then you count what is inside, right? And then there is a chi-square test to determine independence. Okay, so we don't have the time to fill out this, but if this is filled out, you know what to do, right? You'll use a chi-squared 16, because it's 4 times 4. Degree of freedom is 16 here, and you can calculate each of these buckets and their intersections. Okay, so I'm curious to know the answer to this question, right? If those of you who have the time and energy to fill up this matrix and actually do the computation, please start a discourse thread on this and put out the answer. You can tag me also. I can go in and write down. I'm curious to know the answer to Q7 and Q8. We don't have to do it now. It's an exercise. You can do it, and then conclude on whether or not age is independent of CG in our class, in our Stats 2 class, based on the 49 samples. It may not be enough samples, but still maybe we can come to some sort of a conclusion. Okay. Somebody is very upset in my house. I don't know if you can hear it. Okay. All right. So that is probably my cue, and I think that's the last slide I have as well. I hope you enjoyed it. I think it should be useful for you in the exam as well. But primarily, I think almost all of statistics is estimation and testing. Okay. And the ability to think of these things correctly in the proper way and understand them well and use it in situations in a proper, correct way and not get misled is absolutely vital. And I hope some part of that was conveyed to you in this exercise. Okay. Thank you very much for participating, and we can okay, so okay, so I think some people are asking for another session with the instructors on doubts for preparing for exams. I will ask the instructors to do a couple of live sessions, or 1 or 2 live sessions before this. Okay. Okay. Thank you very much, and bye-bye.